Continuing with the compressible flow. Okay, so in the last lecture we are discussing something about converging and diverging nozzle, and why we are going to analysis the converging diverging nozzle in the thermodynamics because of the application in the aerospace industry, and most of your steam turbines or gas turbines we use converging diverging nozzle at the end of the exhaust systems. Okay, so in the last lecture we already derived two equations which relate to isentropic flow for the variation of fluid property with the flow area, and that is for the isentropic condition. Okay, so this is the equation which we already derived, and this is also the equation which we already derived in the last lecture. Okay, so as I hope you already know that what is the meaning of this equation, that this is dA, which is a change in area, dP change in pressure, Mach number, and rho density, and v square velocity. Okay, so here there is a change in velocity, this is v, this is dA, this is a, okay, area, and this is how we can just reference that how your properties variation of fluid property with the flow area. Okay, so now we just try to apply these equation on the two different geometries. Okay, so as you see in this figure, okay, so first figure we have the nozzle, okay, and then there is a diffuser. So the nozzle where the outlet area and outlet opening is less as comparison to the inlet opening. Okay, so in this nozzle we have opening is bigger as comparison to the outlet, and in the diffuser our inlet is smaller, or your inlet opening is smaller in size as comparison to the outlet. Okay, so this is just a basic difference between the nozzle and diffuser. Okay, and then we take different cases. For example, we take subsonic flow and supersonic flow. Okay, and then we can analyze four different cases. So two cases of subsonic flow for the nozzle and diffuser, and two cases for supersonic flow for the nozzle and diffuser. Okay, so basic purpose of this is to analyze that how our properties varies with the change in area, okay, or with the change in geometry. Okay, when we transfer from nozzle to diffuser, or either we can change from subsonic to supersonic flow. Okay, I hope you already know that subsonic flow means your Mach number is less than 1, and supersonic flow means your Mach number is greater than 1. Okay, so this is just a basic difference between these two. Okay, so as you notice that there is some arrow which is mentioned over there, which is in the red color. Okay, so the arrow with the upper side, so for example, if the arrow is like this, so it means there is an increase in something. If the arrow is down, so it means there is a decrease in something. Okay, so here, if you can notice, there is mentioned u, which is the velocity basically. So this is v. So in the nozzle case, when there is a subsonic flow, your velocity increase at the outlet. Okay, and if the velocity increase, so definitely Mach number also increases, because your local velocity and Mach number is directly proportional. Then, if you can notice over there, the pressure decrease when there is a subsonic flow, when the Mach number is less than 1. Okay, so I will explain with the help of equation as well. So just I'm giving you a brief information about it, that what is the meaning of this figure. Then temperature also increase at the outlet, then density also increase at the outlet when there is a subsonic flow and when there is a case of the nozzle. Similarly, if we just move towards the supersonic flow, when we are going to increase the Mach number, so after increasing the Mach number with a greater than 1, similar case for the nozzle, we get the decrease in velocity at the outlet. Similarly, Mach number also decreases, pressure increases, temperature increases, and density also increases. Okay, so these are two cases for the nozzle, for subsonic and supersonic. Now, if we change the geometry to diffuser, where there is an inlet opening is smaller as comparison to the outlet opening, so we get the velocity decrease at the outlet. So Mach number also decrease, pressure increase at the outlet, temperature increase, and density also increase. But if we move towards a supersonic flow, we get the increase in velocity, and then there is an increase in Mach number, then there is a decrease in pressure, there is a decrease in temperature, and there is a decrease in density. Okay, so how we get to know that there is a decrease in pressure, there is an increase in temperature when we are changing the geometry? So we will just look at each case individually so that you will get some understanding, and we apply these two equations in order to understand this. Okay, so for example, so first equation we already see in the previous classes. This equation we already derived. So 1 over rho dP is equal to minus v dv. Okay, and from this equation we can easily say that when velocity increases, so for the case and dv is greater than 0, which means it is a positive. If it is positive, then the pressure decreases. Okay, so this comes from this equation. Okay, so if this is your positive, so this whole term become negative. Okay, so because this minus shift from here side, so over velocity, increase in velocity, so pressure is decrease. Okay, so this is just for the uh, case which we already discussed in the previous lecture, and this is the equation which we get from the previous lecture. Okay, so now in the case if velocity is decreased, so for example this term dv become negative now, so it is negative, and if it is negative, so your pressure increase because this term become dp become positive. Okay, because negative negative become positive, so your dp become greater than 0 in this case. So this is just for your basic understanding. Okay, so how we get the, if there is increase in velocity, pressure decreases, and if there is a velocity decrease, there is a pressure increase. Okay, so now we check the cases individually. Okay, so for example, in your first case, we have the nozzle. Okay, and that is the subsonic nozzle. Okay, so subsonic nozzle means your Mach number is less than. Okay, so from this equation, first thing is that Mach number less than 1. Okay, so if you put Mach number less than 1 in this equation, okay, so it's mean this term become positive. Okay, because Mach number less than 1, so this term become positive. Okay, now here for the case of nozzle, okay, so your dA is less than 0. Okay, so how your dA is less than 0? Because your final area is less than initial area. Okay, if your final area is less than initial area, so it's mean your dA is less than 0. So this comes from, so for example, dA is equal to, you can say area final minus area initial. Okay, so if your area final is smaller and area initial is larger, okay, so it's mean this term become negative, and from this we can say that dA is less than 0 for the case of nozzle. Okay, so dA is less than 0 in the case of nozzle. So if you put that value over the equation, you can say equation number 1. So this term is also negative. Okay, and if this is negative, so this negative negative will be cancelled and your dV become positive. Okay, so due to this, your dV is greater than 0 for the case of subsonic flow, and your velocity increases. Okay, and area decreases, which you already do, and when your velocity increases, your pressure decreases, which we already discussed in the previous slide. Okay, and also you can get to know that how your pressure decreases. Okay, you can easily find from the equation which we already discussed in the last lecture, that dA divided by A is equal to dP divided by rho V square 1 minus max T. Okay, and from this we can easily find that your dP become negative when your Mach number is less than 1 and dA is less than 0, because this term become positive if your Mach number less than 1. Okay, and this become negative. Okay, and due to this your dP become negative, so it means your pressure decreases in the case of subsonic nozzle. Okay, so this is just application of these equations. So if you have any question, you can ask me. I hope you will get some understanding of it. Okay, so another important thing is in the case of your subsonic nozzle, uh, due to the decrease in pressure, okay, pressure decreases, so temperature also decreases, density also decreases. Okay, and how we get to know? You can easily, because this is a isentropic case, so you can just apply this equation that T2 divided by T1 is equal to P2 divided by P1, K minus 1 divided by K is equal to rho 2 divided by rho 1, K minus 1. Okay, so these equations are valid for the isentropic process, and from here you can easily judge that if your pressure decreases, okay, so it's mean T2 also decrease and rho 2 also decrease. Okay, so pressure is interlinked with the temperature and your density in the case of isentropic. Okay, so from this we get the some understanding. Okay, so this is the first case. Now we will move towards the second case. Okay, so in the second case, we just take supersonic diffuser. Okay, so supersonic diffuser means the Mach number greater than 0 and your area diverges. Okay, because your area will be increased at the opening side. So that is the diffuser. Okay, so similarly, we just put the values in this. So in this case, your dA is greater than 0. Okay, so it means it is positive. Okay, in the case of diffuser, because your final area is greater as comparison to the initial area. So that's why your dA is greater than 0. Mach number is greater than 0. So if you just put so if we just put these values into this equation, so we can easily judge that the velocity increases. Okay, because this term become negative. Okay, because if your Mach number is greater than 1, this term become positive because dA is greater than 0. Okay, and then if we can just analyze, so dV become also positive. So your velocity increase. Okay, and in the same case, so your dV is greater than 0 for the case of supersonic diffuser. In the case, there is area also increase for the supersonic diffuser as well, and then pressure also decrease. Okay, so pressure decrease you can again find from the same equation. So dA divided by A is equal to dP divided by rho V square 1 minus max P. And from this, you can easily figure it out that your pressure decreases. And if your pressure decreases, so it's mean your temperature for the isentropic condition also decrease, and your density also decrease. And in this case, Mach number also increase at the outlet. How Mach number increase? Because your velocity increases. Okay, so this is how you can figure it out. Okay, so now in the next case, which is the supersonic nozzle. Okay, because subsonic nozzle we already discussed. Okay, so in the subsonic nozzle, again it is the nozzle, so dA is less than 0. Then now the Mach number is greater than 0 because it is supersonic nozzle. Okay, so if you put all these values into this equation, so you will get decrease in velocity. Okay, for the case of supersonic nozzle, and your area already decreases, so pressure increases. So if pressure increases, your temperature also increases, and density also increases in case of supersonic nozzle. The diffuser one, okay, and Mach number is less than 1. Okay, because it is a subsonic flow. So from here we can easily say that velocity decreases at the outlet, area increases, okay, and your pressure increases as well. Okay, and pressure increases, you can figure it out from the equation dA by A is equal to dP divided by rho V square 1 minus max square by just putting the value Mach number less than 1 and dA greater than 0. Okay, so from here you can easily figure it out. So pressure increases, your density also increases, and your temperature also increases, and your Mach number also decreases because of the velocity decrease. Okay, so this is how you can apply these equations in the nozzles and diffusers. Okay, so if you have any question, you can ask me. Then we will go to the next. So this is just a summary of all these things which I already discussed. Okay, that how for the case of nozzle in the subsonic and the case of diffuser for the subsonic, so how your different parameters increases or decreases, and you can correlate with the two equations. Okay, similarly in the case of supersonic flow, you also figure it out how your pressure and all the parameters are increases or decreases when there is a change in geometry from diffuser to nozzle or nozzle to diffuser. Okay, so now coming towards another important point over there is that variation of fluid property with the flow area, okay, and specifically critical property. Okay, so in the previous lecture we already derived some equation for the stagnation property, and okay, so in the last class one student pointed out that the question that I have assigned in the previous class, the values are not similar if we calculate from the equation these equations, and if we can compare with the isentropic equations. Okay, why the answer is not similar? The reason is I have just figured it out after assigning that question that in the last question your Mach number become greater than 1. Okay, and all these equation is valid for Mach number less than 1. Okay, so that's why compare with the isentropic equation, so it will be not accurate. But still we can use this equation if your Mach number is greater than 1 by just putting some assumption, and you can just write if you can figure it out these type of question in the exam and your Mach number is greater than 1. So you can just write one statement that the compressibility effects are negligible. Okay, and then you can directly apply this equation. Okay, so it is acceptable. But if you cannot write that the compressibility effects are negligible and your Mach number is still greater than 1, so it's mean that you're not doing the right thing with the question. Okay, so that's why this is an important point, because when there is Mach number greater than 1, so your compressibility effects are the significant. So that's why we have to take it along in the equations as well. Okay, so that your answer will be accurate. Okay, but because this is not advanced course, so that's why I'm not going towards the derivation of the equation where there is a compressibility effects need to be considered, and that is for the Mach number greater than 1. So for this, you can just note down these equations, and I will try that all the questions which I will give in the exam, make sure that the Mach number will be less than 1, so that you can apply directly these equations. Okay, so these are the stagnation properties which we already discussed in the last class in the previous lectures. Okay, so now here an important thing is that the critical properties. So what are the critical properties? Basically, critical properties are any properties, and that is if you are considering nozzle, if you are considering diffuser. So we can just denote the critical properties at T star. T star. So just a small star with the property, and you can denote as a critical property. And critical property is basically for the specific Mach number, that is Mach number is equal to 1. Okay, and your Mach number is mostly equal to 1 at the throat. Okay, so this is just a throat, and at the throat area, your Mach number become equal to 1. Okay, in the case of your nozzle, and for example, this is the case of converging diverging nozzle, which is the second case. So this is your throat. Okay, so at this point, your Mach number become equal to 1. Okay, so these properties, so whenever you have to calculate the property at the throat, so that you can just correlate that these are the critical properties. For example, if I want to find temperature at the throat, so I can say that the T star I have to find. So similarly, T star, rho star, okay, that is the critical properties. Okay, so in this equation which we already tried in the last lecture, so you just have to put the value Mach number is equal to 1, and you will get the T star by T naught, T star by T naught, rho star by rho naught. And if you can just put the value Mach number 1, so you will get these values easily. Okay, so this is how you can get the critical properties. Okay, so if you have know the stagnation temperature and you know the fluid P value, so you can easily figure it out the value of critical property where there is a Mach number is equal to 1. So similarly, in case of T star, okay, which is the pressure at the critical point or throat. Okay, so you can, if you know the stagnation pressure, so you can easily find the pressure at the throat, and also you can easily find the density also for the critical density, which is at the throat or where the Mach number is 1 by using this relation. Okay, so these are the some important relation in order to find the critical properties. Okay, so in the similar way, we have some more equations which we have derived for the nozzles. Okay, so which is how to find the mass flow rate. Okay, so if you have the different, okay, so this equation we already we will try to derive also in the coming slide. So do not worry that how this equation comes from. So just for your understanding, say that from this equation, if we have the data available, that your area, okay, Mach number, stagnation ratio, K, R, stagnation temperature, specific heat ratio. So you can easily find the mass flow rate at the nozzle. Okay, and at any area, if you have an area, you can easily find out. Okay, but if we have to find the mass flow rate at the throat, so simply you have to plug the value Mach number is equal to 1, so you will get the m dot, and at the throat the mass flow rate is maximum. Okay, so whenever you have to calculate the mass flow rate at the throat, so you can say it is the maximum flow rate. And for example, if in the problem statement it is mentioned that you have to find the maximum flow rate, okay, so it's mean we are talking about the flow rate you have to calculate at the critical point, okay, where you have to find all the properties of the critical property, that is temperature, pressure, and density. Okay, so we will also try to derive these equation. And then another important equation is that which is the last equation. So this is A by A star. Basically, A is the area. So any area over there, and for example, this area. Okay, so you can take any area, and you can take the ratio with the area at the throat. So this is A star basically. So at the throat, you can denote A star, and at any point of your nozzle, okay, other than A star, you can just denote A, which is the area. So this is the equation in order to find the these ratio, which is the area at any point of your converging diverging nozzle, and then with the throat area. So this is one of our Mach number. So Mach number, if you can know, you can easily figure it out, and K value is known to you, so you can find these ratio easily. Okay, so these are some important equations which you have to note down. Okay, so if you have any question, you can also ask me, and then we will. Okay, another important point over there is effect of back pressure on mass flow rate. Okay, so here important point is what is the back pressure? Okay, basically back pressure is any pressure at the exit of your nozzle. Okay, so for example, this is your exit. Okay, and we just denote as a PB. Okay, so PB is basically pressure at the exit. So sometimes we call it as a P exit, and we call it as a PB. Okay, which is the back pressure of the nozzle. So we can just take one case, or five different cases basically. Okay, and we will find out that how your back pressure is affected with the increase in pressure. Okay, so for example, in the case one, and this is one graph with the m dot versus PV by P naught. So PV is basically back pressure, which is at the exit of your nozzle, and P naught is the your, you can say, stagnation pressure also. Okay, because this is the point where we have to start the flow. Okay, so PB by P naught. So in the case one, your PB is equal to P exit is equal to P naught. Okay, so you can easily judge that because there is no pressure difference, so it's mean your flow is zero. Okay, so if your PB is equal to P naught, so it's mean this term become 1. Okay, and this is your point number A. Okay, and your mass flow rate is also 0, because if you can judge that from here the mass flow rate is 0. So this is your case A. Now moving towards case B and C. Okay, so here what we have done is we have just decreased the PB. So where we have to just down the value of back pressure. Okay, and the mass flow rate increases. Okay, so if you can notice from the graph. Okay, so this is your point number B. Okay, so as you are increasing the pressures, you are decreasing the pressure. Okay, so your flow rate, mass flow rate increases, and flow is subsonic throughout. Okay, and this is the point C and D where your um, okay, so where the flow is subsonic and the pressure at the nozzle exit equal to back pressure. Okay, so whenever it is mentioned that the PB is decreased and your flow is subsonic, okay, so it's mean that your back pressure become equal to exit pressure. Okay, so this is just some important point. Now for the case D. Okay, so if you can notice the point D over there, so this is your point number D. Okay, so eventually as PB is decreased, okay, so we are just further decreasing the back pressure. Okay, so if we more decrease the PB, so at some point we get the Mach number as unity. Okay, so and is attained at the nozzle exit, and the corresponding exit pressure is called critical pressure. So any pressure at this point where your Mach number become unity, so we call it as a critical pressure, and we can denote as P star. There's a similar thing if you get the other property for T star, rho star at the point number D. Okay, so and the mass flow rate is maximum possible. So at this point, your mass flow rate is maximum at the critical point. Okay, and the nozzle is said to be choked. So what is the meaning of choked? So choked means basically when your mass flow is maximum and cannot increase further by changing the back pressure. Okay, so this is the meaning of choke flow. So if you can just increase more pressure after this point D, okay, so you will not see any effect on the mass flow rate. Okay, so mass flow rate does not change at this point. Okay, so we can say that this region D to C, you get the choke flow, and for the region where there is a C and D, so that is not choke flow. Okay, so this is just some important information because this you have to use for. Okay, so KC is mentioned over there. Further reduction in PB below critical pressure have no effect on the flow condition within the nozzle, and mass flow rate does not change for this condition. Okay, so if you have any question, you can ask. Okay, so now we will try to derive the equation which we already discussed in the previous slide. So this m dot and a by a star. Okay, so that you will get some understanding of that how these equations come from, because you have to use these equations in the further analysis. Okay, so for example, we just take one case at this is your converging diverging nozzle. Okay, and at this point your Mach number is 1. Okay, and just one case for this. Okay, and for this we have to find the ratio, that is area at any point and area star. Okay, so our main target is to find a by a star relation first. Okay, so how we have to find this a by a star relation? Okay, so we can just simply apply the mass flow rate balance. Okay, so mass flow rate, because this is a steady flow, so we can say that the mass flow rate is almost equal. Okay, so we can say that rho VA is equal to rho star V star A star. Okay, so rho VA is at any point and star basically at the critical point, which is at the throat point, where there is a Mach number is equal to 1. Okay, and from here we can simply say that A by A star is equal to rho star divided by rho multiplied by V star divided by V. Okay, so we can write it in this form. Okay, so from here we already know rho star by rho. Okay, basically this is the you can say this point as a stagnation point as well. Okay, so just for the reference. Okay, and we already know that the rho star divided by rho is equal to 2 divided by k plus 1 divided by k minus 1. Okay, so this equation we already seen in the previous slide. Okay, that how you have to plug the value Mach number equal to 1 in the stagnation property value stagnation equation, and you will get this equation. Okay, so simply you have to put this value into this equation. Okay, so now we have to find. Okay, so wait a minute, I have to. So in the equation, this is P naught. Okay, here this is rho naught, and here this is the density. Okay, so that is not a stagnation density. So we cannot simply put this value into this equation. So in order to find the rho star divided by rho, what we have to do is we just write like this, that rho star divided by rho naught. Okay, so multiply rho naught divided by rho, which is the local density, because this is the local density, is not a stagnation density. Okay, so we have the value of this from this equation, and this comes from the equation for the stagnation property, where we have already find the value of the ratio of the stagnation property to the local property. Okay, and you just have to simply put these values and you will get some equation as. So you just have to do it by yourself. I'm just going to write the final equation. So 2 divided by k plus 1, 1 plus 1 by 2, k minus 1, max square 1 divided by k minus 1. Okay, so this is the value of rho star divided by rho. Okay, so by just simply putting the two different equations. Okay, so now we have to find the V star by V also. Okay, so then we get the A by A star. Okay, so in order to find V star by V, so V star divided by V. So we can simply write that this is KR T star 1 by 2, because under root KRT, which we already see. Because here the Mach number is 1. Okay, so your speed of sound is equal to your local velocity. Okay, so that's why we just say that your V star is equal to KR T star 1 by 2. Okay, and in the denominator we have the V. Okay, and if we can further simplify this equation, so we can also write that kr t 1 by 2 over local velocity T star over stagnation temperature 1 by 2 T naught divided by T 1 by 2. Okay, so simply if you can just figure it out, if you can simplify, so these two equations are equal. Okay, I'll just make these equation equal. So now simply what you have to do is you already know this value T star by T naught, okay, from the previous slide, and also you have already know T naught by T value from the previous slide. So you have to put these values into this equation, okay, and there is some equation which we get as V star divided by V as 1 mach 2 divided by K plus 1. Okay, so this equation you have to just put and do this solution by yourself. Okay, I'm just going to write the final equation. A minus 1 max square and 1 by 2. Okay, so this is the equation for V star by V. So we have now two equations. So if we have these two equations, simply you have to put these equations into, you can say equation number 1, and you will get the value of A by A star easily. Okay, so there is no difficulty in this. Okay, so you have to note it down and then we'll move towards the next one. And also all the difficult equations which we derive, I will try to put this in the formula sheet, which I will provide in the exam as well. Okay, so you do not need to remember all these equations. Okay, so only for the difficult one. So simple equation I will not provide, but the difficult equation I will definitely provide with this. Okay, so by just plug in all the values, so you will get the equation which we can already see, which is 1 over mac 1 plus 1 by 2 k minus 1 mac inverse square 1 by 2 k plus 1 2k minus 1. Okay, so this is the equation which we already see in the previous slide. Okay, so this is how you have to find the ratio for your area, which is at any point, and then the plot area. Okay, so if you have the value of these things. Okay, so you have to note on this equation. Then we will try to derive another equation which is called the mass flow. This equation we will try to develop. Okay, so mass flow rate, you already know that mass flow rate is equal to rho A V. Okay, and from here we can simply say that rho is basically E divided by RT, area is A. Okay, so just you are considering a simple case of your conversion diversion nozzle, or you can just mark as this your A star, and we are finding the mass flow rate. Okay, so here when V is basically MA into under root KRT. So by defining the Mach number, so Mach number is basically V by C. So V is equal to Mach into C. Okay, so from here, if we can further simplify this equation, so this equation becomes P A Mach number under root K divided by RT. But this is just by simplifying this equation. Okay, so from here, if you already know the relation of stagnation property, so for stagnation property, so we already developed P naught divided by T is equal to 1 plus K minus 1 divided by 2 max square K divided by K minus 1. From here, if we have to find the P value, so which is the local pressure, so P is equal to basically P naught divided by 1 plus K minus 1 divided by 2 max square or K divided by K minus 1. Okay, simply you have to plug this value into here. This you can say first equation. So similarly, you have to plug the value of T as well. Okay, so where you get the value of T? So again, from the isentropic for the stagnation property relation. So T naught divided by T, 1 plus K minus 1 divided by 2 max square, and from here you will get the value of T. Okay, and T naught will be in the numerator and rest of the all the things in the denominator. Okay, so from here you get the value of T as well. So you have to plug T value and P in the first equation. Okay, so then you will get the mass flow rate equation. Okay, so just you have to note it down, and then I will move to the next. So the final equation become mass flow rate by just plug the value of T and P in the first equation. So that is A max P naught K divided by R T naught, and in the denominator we have 1 plus K minus 1 max square divided by 2 K minus 1 to K minus 1. Okay, so simply if you have you know the value of area, you know the Mach number at that point, you know the stagnation pressure, you know the stagnation temperature, uh, gas constant if it is air or any fluid, okay, and specific heat ratio. So you can easily find the mass flow rate at any point. Okay, similarly, if we have to find the maximum mass flow rate, okay, so I already told you maximum basically mass flow rate is at the throat or where the Mach number is 1. Okay, so if we just simply put the Mach number equal to 1, okay, so we get the maximum flow rate, and at the Mach number 1, your area is basically A star, which is the critical area. Okay, and you can say throat area. So we can just write the maximum mass flow rate equation as by plug the value of Mach number 1 and replacing A by A star, and rest of the equation become K divided by RT naught to K plus 1, K plus 1 divided by 2, K minus 1. Okay, so this is the equation for your maximum mass. Okay, so these are the important equation because if we have to find in most of the problem statement, which we will see in the coming slides, so we have to find the maximum flow rate. Either we have to find throat area, or either we have to find other parameters. So you can simply use these equations in order to find this. Okay, so if you have any question, you can ask me, and then move to the next. So now here is your first example related to the critical properties. Okay, so this is 17-4. So calculate the critical pressure and temperature of carbon dioxide for flow condition described in the example 17-3. Okay, so 17-3 we already solved that example. Okay, so we get all the stagnation property, that is the P naught and T naught from the previous example, and our main target is find the critical property, that is P star, T star at the top. Okay, and you can say where the Mach number is 1. Okay, so you have to note down the data, and then we will see how to solve. Okay, so this is a very simple question. Okay, so just I will quickly draw the schematic over there. This is just a nozzle, conversion diverting nozzle. Okay, so we have stagnation properties, that is 1.4 megapascal. So this comes from the previous example, and T naught is equal to 473 Kelvin. So the main target is to find and the properties at this point, which is the critical point. Okay, so simply you have to apply the relations which we already developed in the previous slides, which is the critical temperature over T naught, okay, which is a stagnation temperature, is equal to 2 by K plus 1. Okay, so this equation we already see. I just plug the Mach number is equal to 1 in the stagnation property equation. Okay, you get the equation. Okay, so here we have the carbon dioxide. So K value for carbon dioxide is 1.289. So you will get from table A2 easily. Okay, so simply you have to plug the value. So you will get the ratio of T star by T. So 1.289 plus 1, and which is equal to 0.8736. Okay, similarly, you have to find the T star by P naught. Okay, because if we have these ratios, so then we can easily find the temperature at the critical point and pressure at the critical point, which is P star and T star. So similarly, we can just say that P star by P naught is equal to 2 divided by K plus 1. That is K divided by K minus 1. Okay, and from here you can easily plug all the values, and you will get 1.289 plus 1 and 1.289 divided by 1 minus 1.289 minus 1. Okay, so you just have to solve it by yourself, and it will be equal to 0.54%. Okay, so now we have the ratio of the critical temperature over the stagnation temperature, and ratio of critical pressure to stagnation pressure is known to us. So simply you can say that T star is equal to 0.8737 into T naught, and P star is equal to 0.5477 into P. So P naught and T naught value is mentioned in the question. So simply you have to plug the value, and you will get the T star and T star. 8737 into 473 and 0.5477 into 1400 kilopascal. So you just have to solve these two, and you will get T star as 413 Kelvin and P star as 767 kilopascal. Okay, so this is two are the required thing to find. So this is how you have to find the critical properties where there is a Mach number is equal to 1. If you have any question, you can ask, you can note it down, and then we'll move to the next question. Okay, so here is the next example, which is example 17-5 from your book. Okay, so you have to read the statement first. So air at 1 megapascal and 600 degrees Celsius enter a converging nozzle shown in the figure with a velocity of 150 meter per second. So determine the mass flow rate through the nozzle for the nozzle throat area of 50 centimeters square, and when the back pressure is 0.7 megapascal and B 0.4 megapascal. Okay, so this is our data, and you have to note it down, and then we will try to solve it. So now we will try to solve it. Okay, so first thing is here that you have to determine the mass flow rate. Okay, so in order to find the mass flow rate, first we need to find the stagnation properties. Okay, so in order to find stagnation properties, so we can apply some relation. So first we can just there is a nozzle over there, okay, so which is our question. So you can say initial, so which is 1 megapascal. Temperature initial is equal to 600 degrees Celsius, and your VI is equal to 150 meter per second. Okay, and this is your throat. Okay, so where there is a back pressure. So, so this is your back pressure, and we have to find the mass flow rate for two different back pressures, which is 0.7 megapascal and 0.4 megapascal. And your throat area is also mentioned, so you can just say that your area throat, so area T is equal to 50 centimeter square. Okay, so this is our data which is available from the question. Okay, so now first thing is we have to find the stagnation properties, because we need, in order to find the uh, exit, your velocity as well, and also your uh, density at the exit. Okay, so we will figure it out why we need these T and rest of the stagnation properties. So first we can simply apply that stagnation at temperature, and you can say at point number I, because this is the initial condition and we have to find the property where the velocity is 0 first. So here we can say that Ti plus Vi square divided by 2 Cp. Okay, and from here we have the value of Ti with us, Vi value is with us, which is the inlet velocity, and 2 Cp. Okay, so simply you have to plug the value, so you will get the required thing, which is the stagnation equation. So I'm not going to plug all these values, so you have to plug it by yourself. So I'm just going to write the final value. Similar thing, you have to find the stagnation pressure as well. The stagnation pressure, so simply you have to apply the isentropic relation. So P naught over Ti is equal to T naught over Ti K divided by K minus 1. Okay, so you have the value of T naught from the above part. Ti is mentioned in the question. Pi is also mentioned in the question. So you can simply find the value of V naught by using this equation, and which is equal to 1.045 megapascal. Okay, so now we have the stagnation property, both T naught and P naught. So this is P naught. Okay, so first thing is for the part A and B, so you have to find P star by P naught, because from P star by P naught we can easily find, because our main target is to find mass flow rate. Okay, because if we have to find the mass flow rate and we do not know that our P star or P naught value, so we cannot judge that our flow is maximum or the flow is what type of equation we have to plug. Okay, so that's why we just simply use the P star by P naught first. Okay, so that we will find out our flow is choked or either it is not choked. So P star by P naught basically come from 2 divided by K plus 1, K divided by K minus 1. Okay, simply you have to plug the value for the air value, K value. Okay, you will get P star by P naught as 0.528. Okay, so this is our P star by P naught value. Okay, so now here you have to calculate first P by P naught value also, because if you remember from the graph which we discussed while discussing the nozzle, okay, so we get PV by P naught, and from PV by P naught we can easily judge that our flow is either choked or it is not choked. PV by P naught. So PV value for the part A, okay, so we just write that it's the part A is 0.7, and your P naught value is 1.045, and there you get the PB by P naught value as 0.670. Okay, so if you can notice that this value is greater than your critical pressure ratio. Okay, so thus the exit plane pressure or your throat pressure is equal to back pressure. Okay, so this we already discussed in the graph that when this value, your P star by your PB by P naught is greater than the critical pressure ratio, so your back pressure become equal to exit pressure. Okay, so that's why we are trying to check this by using P star by P naught. Okay, so you have noted down and then move towards the further solution. Okay. So here, if this condition is satisfied that PV by P naught is greater than P star by P naught, okay, so from here we can easily say that your throat pressure is equal to back pressure, or you can say exit pressure is equal to back pressure. This is 0.7 megapascal. Okay, so from here we have to find some important point over there, that your PT by P naught. Okay, so I will give you the explanation that why we need this type of value. So PT by P naught, which is your exit or you can say throat pressure over stagnation pressure ratio. So this is your, okay, so if you can just plug the value 0.7 divided by P naught value, you have already found. So you will get the ratio as 0.670. Okay, so this is our reference value. Okay, so why we need this value? Because we have to find and different properties, okay, by using thermodynamic table. Okay, and I will just give you an overview that which thermodynamic we need. Okay, so you just have to remember that PT by P naught value you have already found. Okay, so just you have to go to the thermodynamic table. So here it is mentioned table A32. So one dimension asymptotic compressible flow function for ideal gas with K is equal to 1.4. Okay, so simply you have to shift to table A32. Okay, so here is your table A32. Okay, so you notice that here all the formulas are given, which you already seen in the previous lectures. Okay, so here this equation say this table says that there is different properties uh, that is given for different Mach number. So we have Mach number here, and then we have Mach star. Okay, so this is an important point also, that what is that Mach star? Okay, so basically Mach star is your local velocity over speed of sound at your throat. Okay, so and if you have to calculate Mach number at that specific point, so we can just denote as Mach star. Okay, and then A by A star. So this you already see that what is the A star, which is the critical. So this is P by P naught. Okay, so this P is basically your exit pressure, or you can say, and this is your P naught, which is the stagnation pressure. So rho over rho naught, P by P naught. Okay, so from if we can just go back to your question, so we already get P by PT by P naught, which is 0.670. Okay, so if you can figure it out where your PT by P naught here, okay, and this is 0.670. So it's mean that 0.670 lies in between these 2 points, 0.7029 and 0.6560. Okay, so what you have to do is you have to just apply the interpolation and you have to find the Mach number, and also you have to find T by T naught. Okay, and from this setup we will find the mass property. Okay, so this is the procedure you have to follow from table 830. Okay, so I'm just moving towards the problem again. Okay, so from thermodynamic table and by using the interpolation by using P by P naught value, which is 0.670, we get Mach number. You can say that Mach number at thought, okay, which is equal to 0.778. Okay, so this comes from interpolation. Okay, so this you have to practice by yourself. So T by T naught. Okay, also we have to find. So by applying second interpolation, so which is 0.892. Okay, so we have these value now. Okay, so because we need the value of mass flow rate. Okay, so in order to find the mass flow rate, we need the velocity at thought. And if we need the velocity of thought, so then we need the temperature at also thought. Okay, so first we have to find the temperature at thought. So temperature at thought is equal to 0.892 into T naught. So T naught value we have already found in the previous step. Okay, so simply you have to plug the value 0.892 and T naught value is 884 Kelvin. Okay, so which we already figured out in the previous slide. So from here we get the 788.5 Kelvin, which is your temperature at the throat. Okay, so from here we can simply figure it out. What is the value of velocity at the throat? So velocity at that throat come Mach number at throat. Okay, so which we already find from the thermodynamic table, and also speed of sound at the throat. So Mach number at throat into under root Kr temperature at the throat. Okay, so Mach number at throat known to us, K value is known to us, R value is known to us from thermodynamic table, and temperature at throat we have just found. Okay, so simply you have to plug the value and you will get the required thing, which is 0.778. Then this under root 1.4, 0.287 into 1000 convert into joule, and then 788.5, which is the throat temperature, and we can figure it out that this will be 437.9 meter per second for your velocity at the throat. Okay, so if we have the velocity, so we can easily find the mass flow rate. Okay, but for mass flow rate, we also need the value of density. Okay, so you have to note it down, and then we will find the density first, and then we will go towards the mass flow rate. Okay, so we can find the density at the throat, which is Pt over R, temperature at the throat. So pressure at the throat is 700 kilopascal, which is we call that pressure is equal to throat pressure. So 700, you can say kilopascal, and then R value is 0.287, and temperature at throat is equal to 788.5, and this is equal to 3.093 kg per meter cube, which is the density of the throat. So from here we can easily find the mass flow rate, which is equal to density at throat, area at throat, and velocity at throat. So density at throat is 3.093. Area of throat is mentioned in the question, which is 50 centimeters square, so 50 into 10 raised to the power minus 4. And velocity at throat is 437.9. So this become equal to 6.77 kg per second. Okay, so this is the first part in order to find the mass flow rate when your back pressure is equal to 0.7 megapascal. Okay, so if you have any question, you can ask. Then we move towards the part B. So in the part of the B, simply we have to reduce the back pressure by 0.4 megapascal, and similar thing we have to find the mass flow rate. Okay, but the procedure is different. Why? Because if you can just simply apply the check of your dP by back pressure by P naught value is less than the critical pressure in this case. Okay, so if we can just find out that BP by TP P naught, which is the back pressure 0.4 megapascal over 1.045 megapascal, which is equal to 0.383, and our P star by P naught value is 0.528. Okay, so our BP by P naught is less than P star by P naught. Okay, so what is the meaning of this? So the meaning of this is that our flow is become sonic and the Mach number become 1, and the flow become choked, and at the choke flow we get the maximum flow rate. Okay, and when there is a maximum flow rate, so we can simply apply the mass flow rate equation, which we already derived in the previous slide, that is for Mach number 1. So here we can just simply say m dot a star t naught under k r t naught to k plus 1 over to k minus 1. Okay, so this is the equation for the sonic flow, and when we okay, so we have all the values because a star basically or area not is the stagnation pressure. We have this property P naught on the solution. And the question which you have to solve by yourself, I think you will easily solve it. So if you have any question, you can ask them, and then we just stop at this.